Today we continue from the last lecture, and we are going to look at another kind of bifurcation, which is the subcritical Hopf bifurcation. Give me a moment. Yeah. So in the last lecture, we studied the supercritical Hopf bifurcation, where you had a fixed point, and that went into a unstable fixed point and a limit cycle, and we saw that the limit cycle was very gradual, as you change the parameter, the limit cycle radius roughly scaled as so for the supercritical Hopf bifurcation is amplitude of a limit cycle scaled gradually with the parameter. As you tweak the parameter, the limit cycle became larger and larger. Now we are going to look at a slightly more dangerous subcritical Hopf bifurcation. That's the focus of today's lecture. And in general, subcritical bifurcations are more dangerous simply because the system jumps to a distant attractor, and as a result it can be more dramatic as a change in a dynamical system for engineering applications. Dramatic for engineering applications. So let's study an example. So here we take the dynamical system r dot mu r plus r cube minus r5, and theta dot is br square. Now r equals to 0 is a stable fixed point for mu less than 0. You can see that when I linearize the system, only the linear term remains, and for mu less than 0, that's stable. So what happens for mu equals to 0? Well, mu equals to 0, I have r dot equals to r cube minus r5, and r cube now acts as a destabilizing thing, and it becomes unstable as a result. And of course, that's not the only attractor in town. I have this guy as, so there is at r equals to 1 to 1, there is a distant limit cycle. So how does the bifurcation diagram look like? Let's see. So for mu less than 0, I have a fixed point and the trajectories would spiral into it. That's a fixed point I have. And what else do I have? I do have, let's see, I have two more attractors, which is to say two other limit cycles, and where are they coming from? See, so let me write down the equation again for mu less than 0. That's nothing but mu r plus r cube minus r to the power of 5. And of course, r equals to 0 cases there. I can write this as this is a r plus minus r to the power of 4 plus r square plus mu. So I can solve this equation to find the other attractors, and that comes out to be the value of r square should be minus half plus minus 1 plus 4 mu. I'm just solving this equation. This is essentially if I put r square equals to some t, that's a quadratic equation in t. So the quadratic equation, the roots are given by these guys. So I just put this as this guy. So at these values of r, since this is polar coordinates, we are only interested in the positive values of r. So r is nothing but square root of half minus plus this guy. So these are the true attractors. These are the two values. One of them turns out to be stable and the other turns out to be unstable. So I'll just label them. So this attractor was at the value r equals to half minus 1 plus 4 mu by 2. And I have this attractor, which was d plus r was, well, this should be square rooted. Yeah, so I'll put it as half plus 4 by 2. And this turns out to be, this was the unstable limit cycle. And the other guy, this was the stable limit cycle. So that's exactly what's happening. And as you can see, the value of the parameter mu less than minus 1 by 4, these guys become imaginary, so there are no limit cycle attractors. I only have this fixed point. For mu greater than minus 1 by 4, I immediately have these two attractors appearing. And we have a limit by the way, yeah, so essentially that's the thing. And what really happens, so this is the picture at mu less than 0. I have a fixed point which is unstable, the trajectory is, sorry, it's a stable fixed point. I have a limit cycle, all trajectories from this limit cycle uh, either go this way, or, and this is a stable limit cycle, so all the trajectories will come and hit this one, the stable limit cycle over here. So, and of course all these trajectories also go to the stable manifold over here. So this is the unstable one, this dotted surface. Trajectories repel away from it either to the fixed point or the stable limit cycle. That's the picture of the dynamical system for the parameter mu less than 0. Now for mu equals to 0, what's going on is the following. Or you can maybe also look at, let's say we just look at mu greater than 0, that will be more clear. So for mu greater than 0, what happens is that the outer limit cycle is the only stable attractor in the town. So for mu greater than 0, what happens is that this, as you can see from this equation, when you linearize it, for mu greater than 0, the fixed point at 0 loses its stability. Fixed point at 0 loses its stability. And then you are basically left with the only stable attractor in town is the outside limit cycle. So for mu greater than 0, I have these two limit cycles. This was there, and actually even this limit cycle doesn't remain. I'll come to that later. So just follow me for now. This is what happens. So this was the unstable attractor. Sorry, stable attractor. And this was the unstable fixed point. That's the idea. And what actually happens to this unstable attractor? So as I became mu greater than 0, the only thing left in town was this unstable fixed point and this outside stable limit cycle. This seems to have vanished. This attractor seems to have vanished, and that you can actually check. That actually converges into 0. So for example, I had this roots of these equations as r was half plus minus, so I can put r square also, doesn't matter, 1 plus 4 mu upon 2. So this was the thing. So for mu equals to 0, one of the values, so the r minus goes to 0 and r plus is whatever it is. So r square minus, I can put r square plus. It doesn't matter if I am saying the radius of the limit cycle or the square of the radius of the limit cycle, but that essentially is happening. So this was the plus sign, which essentially becomes 1. So this R minus this attractor vanishes. So as I am cranking up mu, from mu less than 0, I had mu less than 0 but mu greater than minus 1 by 4. That was the time I had 3 people in town. The stable fixed point, the unstable limit cycle and the stable limit cycle. For mu equals to 0, this attractor collides with the fixed points and makes it unstable. So I have this unstable fixed point and I have this guy, the stable attractor. And this sort of feature persists for higher values. So right here is the bifurcation we are interested in. As I go from mu less than 0 to mu greater than 0, I go from a stable, this should be a stable fixed point, to an unstable fixed point, and the trajectory jumps on a distant attractor, R equals to 1. There is a sudden transition, not a gradual. So the radius of this attractor is suddenly 1. It's not unlike the supercritical Hopf bifurcation where it gradually changed with the parameter as going as mu to the power of half as I slowly crank up mu. This is a potentially dangerous situation in engineering applications, just changing the parameter. Now my only stable solution is somewhere over here. So that is essentially the idea of the Hopf bifurcation, the subcritical Hopf bifurcation, and we can actually represent it through a bifurcation diagram. So how does the bifurcation diagram look like? I have R, I have mu less than 0. This state fixed point at R equals to 0 loses its stability. This was mu greater than 1. Then one of the crucial points I had was minus 1 by 4, where suddenly I have two limit cycles, one of them the stable one. This was the limit cycle we were talking about, this guy. And then there is an unstable one, which, by the way, gets destroyed. It collides with the fixed point at R equals to 0 and renders it unstable. And this was the this was the stable limit cycle. This was the journey of the unstable limit cycle. And what do I have? This was the bifurcation we were interested in. At mu greater than 0, the system immediately cannot stay here on the unstable thing. It has to jump. So jump I'll represent by a red thing. It has to jump to over here, because this is the attractor. This is the stable attractor. It has to chase that attractor and settle on that trajectory. So this is the progress forward in mu. I can of course write down this guy as we've already discussed. This was R plus square. Journey was half plus 1 plus 4 mu by 2. And yeah, don't need a square root sign. R minus plus 4 this guy. And yeah, so at mu equals to 0, the r equals to 0 fixed point loses its stability. This is indicated by over here. So at equals to 0, r equals to 0, fixed point loses its stability. For mu greater than 0, only the distant limit cycle, this guy, is the stable attractor. And notice something very interesting. Let's say I am doing an experiment and I crank up mu. This guy has to jump to this. The trajectory has to go to over here. Now once I backtrack, so this is the motion forward in mu, the parameter. Now as crack down the parameter, it's not going to follow this path. It's going to follow this part because this was a stable attractor and it's going to backtrack over here. So upon reducing the parameter now back from mu greater than 0 to mu less than 0, it's not going to reach this fixed point. It's going to follow this limit cycle, and finally when these limit cycles are destroyed at mu equals to minus 1 by 4. So by the way, the focus of this chapter was this bifurcation that was occurring at mu greater than 0. We'll follow up this lecture, and this is another interesting bifurcation happening where two limit cycles themselves are colliding and destroying each other. So this is the focus of the next chapter. Well, we pretty much covered it here, but that was our focus of this particular chapter. What happens to the fixed point as I tweak up the parameter, how it becomes unstable, and the trajectory jumps to a distant attractor. So this phenomena, you go forward one way and come back from another path, is known as hysteresis. Check the spelling. Backtracking mu, the parameter, will not lead to destruction of oscillations. Oscillations are continuing in this path. So we also saw here the example of how limit cycles are colliding. Let's take it up in the next chapter. Thank you.